welcome back. Here is Nathalie Wahl to talk about slopes in homological stability.
Hey, thanks. I don't know what actually.
Thank you.
Good job, this is on air.
Okay, maybe for such a pleasant program. Yes, so I'll talk about the slopes in homological stability. My full title said the classical way, so this is a bit referring to Oscar's talk, which was a few weeks ago, where he told us how in homological stability one might improve certain things by looking at these EPA cell structures. I won't get into this, but anyway. So what are slopes? What is homological stability? What do I want to talk about? I'll state two theorems where the difference will be well, the slope, but also the assumptions. So this is in Mazen and Nathalie Wahl. And they tell you that the homology of GLN R is independent of N, or N at least 2 times the degree plus something called SR, R, which is stable range, some range of the ring, okay? And there's a statement, so this is Mazen, and then there's homology of SP2N R, homology of ONN R, and homology of UNN R is also independent of N, or N at least 2 star plus 1 plus something called USR of R, which is, I haven't told you much about this unitary stability, which is some other invariant of R, and here the ring would have an involution for defining unitary groups.
But there's no assumption that 2 is invariant.
No assumption whatsoever. So, you know, I mean, it doesn't say anything if the stable range is infinite, of course, but as long as it's finite, this is the statement. So here's another theorem, Quillen, and then this work with David Sprehn. And what we say is if R is a field which is not F2, which is a field. This is the range, right? This is what we call by the range in which stability holds. Then the range in both cases improves to N at least star plus 1. Okay, so here we need N to be twice the degree plus potentially some constant. Also here, and here we're down to just once the degree plus 1. And this is the slope, is this, of course, the important number in these bounds. Okay?
So SR and USR are not needed. Is
No, yeah, I mean, of course, for fields, it would be 1 or 2. Yeah, it would be a fixed number, but there is no other shift, just a plus 1. And it's the same on both cases. So
Is that where the Milner key theory shows up?
at this number, yeah. The failure where the next, so the subjectivity is one better than the kernel.
So is this best possible?
Yeah, at least in some, yeah. Okay, there are cases where.
If you want a statement for all n, then it's best possible.
Exactly, in this form. So the story is that this statement has been, attributed to Quillen forever. It turned out that it wasn't written in the published manner anywhere, but it also turned out it was in his notebooks, up to a couple of bleach pages, of course. So for GLN, so Quillen did they did the GLN version, and so what we've done is we wrote this up, and then realized that we could use a very similar argument for the other groups. So I'll try to explain what these arguments are like, why the slope, why such an improvement can happen under these assumptions. Before I do that, so some of you have heard part 1 of this talk. This is part 2 of the talk. So I talked about this at the BTM is a little bit what are these orthogonal, unitary, and stuff and groups. So let me just give a 2-minute version of that. So why do these 3 groups show up? So SP, 2, and R, O, and R, and U, and R, the same group. Okay, they're not quite the same group. Just with different parameters. So in an appropriate world, so they all what one could call modes of what you want to group of a certain hyperbolic guy to the n. That's what I mean by these groups. And what is this? So H is so this is we call this a formed space. It's a vector. Or if I'm with a ring, I take direct sum of the ring with itself, and on this I take the sesquilinear form. So R comes with an involution. X goes to X bar, an involution, which could be the identity. Okay, so this is. I'll assume I have an involution, and then I define a sesquilinear form on this. I have been too much working with fields, and I have all sorts of troubles working on rings. But this works for rings. What is this map? It takes x and y to x1 bar y2. Okay. You can define such an object, and then you can talk about the automorphism group of such thing. Okay. Yeah. Well. But then you have to say where this lives. This lives in some. You want to think of this as living in some sesquilinear forms on R plus 2 modulo something. And this something will depend on some parameters, and maybe the other thing too depends on sigma, and depends on an epsilon, and depends on the lambda, where epsilon bar is 1, epsilon is in the ring, and lambda is some additive subgroup, satisfy some conditions.
Is your
What?
R commutative?
I don't think so, no, right?
That is an
No.
anti-evolution.
It's an anti-evolution involution.
And epsilon is central.
And epsilon is in the right place. Okay, so what you need to know about this is if given sigma, epsilon, and lambda, you can associate to such a Q an omega Q, which is also a map is 2 entry, which is defined to be Q x y plus epsilon Q y x star, which is an like epsilon permission form, which should start making you to think of unitary group would be preserving such a form where epsilon would be 1, and this would be the involution. In symplectic group, you would have epsilon minus 1, and the involution would be trivial. And so this is one piece of data you get, and then you get a Q. So this is QQ, which is a map, which is a single entry, which is Q of x up to this lambda. This is an R on lambda, and this is a quadratic refinement. And this is only for fields, this is only important in characteristic 2 in the case of orthogonal groups. So the and the sort of symplectic groups. So SP2N is the case. So the involution is the identity, epsilon is minus 1, and lambda is the whole thing. So there is no quadratic refinement because this is just trivial. O and R is epsilon, sigma is the identity, the involution is the identity, epsilon is plus 1 now, and on the other hand, lambda is 0, so, and actually in this case, everything is determined by this quadratic thing, and U and N is the case where sigma is not the identity, epsilon is 1, and lambda in this case is the invariance. Okay, so it's actually so that's the reason why these three groups keep popping up together, because we need some one group, and we just mistake the theorem we actually prove. Give this one a second. The full theorem is to say that if you look at for any Q, so you fix some setup, you fix some sigma epsilon lambda. Now I'm in fields, okay, over F naught F2. I pick some form which is an element in that thing. Then you can look at the homology of the automorphic group of EQ mapping to the homology of the automorphic group of EQ plus this H that I defined above, and this is an isomorphism of genus of E at least star plus 1, where G of E is what we call the genus, and V is the dimension of a maximally isotropic subspace where Q is trivial minus the dimension of the radical of A, which is like the sort of vanishing of first okay, so this is sort of the general formulation.
Is that the same as the number of hyperbolic signs over a field?
Yes, this is not obvious, right? So so H is non-degenerate of genus 1. So this is like, in this sense, it's a reasonable, it's a typical sort of stability-like situation. We have like something of genus 1 and we're going to plus that thing of genus 1 under some definition of genus, which is this one. And then one can reinterpret this as being the number of cells. Okay?
So this maximum isotropic thing, is that a vector? Do you mean the maximum vector subvector space that is
So U inside, so E is a vector space,
Yeah, and what about you?
U is a subspace.
Okay.
Yeah, so it's a subspace. So isotropic, this is a Q vanishes on it.
Yeah,
And this you have to be a little more careful how you define. And for let me, for simplicity, I'll assume that this I is 0, which is is non-degenerate. So it won't show up for a bit, but it will disappear from now on. You can put it in. It's a little bit painful, but it's possible. Okay, so yeah, so I want to explain how this sort of slope improvement can show up. So we first have to understand why slope 2 was the right slope before, and then we'll see why we can improve it. So this sort of Quillen's stability. Basically, this is, has been very useful. I'm going to get it slightly modernized, maybe version of it. What's the idea is if you have, so suppose you want to study the homology of the automorphic group of some ferrate objects. Okay, so here I'm thinking the vector spaces, which is to study GLN, or these form spaces, Okay, so if you wanna study something like this, and with your favorite object, they should have a notion of rank, a genus, like we had above. So like the dimension of your vector space or the genus of your form spaces. I defined it here. Okay, so suppose you have something like this. For some people, this would be surfaces, and the genus would be the genus. Automorphisms would be diffeomorphisms. It could be all sorts of other things. So what Quillen suggested is that you should make them act on the right type of object in order to have some appropriate spectral sequence. So let's see what it says is find a building X for each object. So let's think of these form spaces X of E with an action of the group G, so the homomorphism group of this thing, satisfying such that for this to be useful, you need that the action is maybe which this should be like maybe a simplicial complex, maybe a semi-simplicial set or something like this, something with a notion of simplices, maybe just a simplicial set, transitive on the simplices where we be. So this is the easiest situation. It doesn't need to be like that, but that would simplify the spectral sequence. To the stabilizer of a P-simplex should be something like just for G of the lower rank object. With a morphing group of a lower rank object, this will allow you to do an induction. Maybe something of rank, your original rank minus P minus 1, that would be the most obvious. Original rank minus P minus 1 would be the typical situation. So for every side of simplices you go down, further down, and 3 that should be highly connected. And that will give you a spectral sequence using this action. I'll give it in a second with a couple of possibilities. Maybe first notes. There is a canonical, I don't know in what sense canonical, but canonical anyway, choice for such X satisfying 1 plus 2 if there is a graded monoidal structure around. This is a bit vague, but you have your favorite objects. If you have a way of taking sums of these objects, and this sum gives you a graded monoidal structure, typically it would often be a symmetric monoidal structure on the groupoid, these objects and their automorphism groups, like we have with vector spaces and direct sum or form spaces and direct sum, then we can actually construct. So this is something Oscar and I do in our joint paper. We have you can simply construct a guy that has these properties. So that's not an issue to find one of these, but then often pretty satisfied, but that's not guaranteed. So, and you have to prove it if it's not, yeah, we don't have
Could you elaborate more on this canonical choice?
I mean, you know, okay, this should be compatible with the rank, right? Let's say the rank increases nicely with your sum. If you want the action to be transitive on P simplices and your stabilizers to be your rank at minus n minus P minus 1, you'll know that the P simplices is going to be the set of P simplices has to be your G, your original G, which is like your Gn, quotiented out by G and minus P minus 1. So as a set, you know exactly what you want. What's not obvious is how should you define boundary maps. If you like, maybe your first boundary map, you know what it is because it sort of comes from the inclusion. You have sort of a canonical way of going between this one and the next guy. So there will be one of the boundary maps will be obvious, and then the braiding will give you the rest. I guess that's the way of thinking of it. And if you apply this to the typical examples, you recover buildings that were built without thinking of it this way in the literature. Okay. So that was one. Yeah. So that was one note. Yeah. Okay. So in principle, if you have such a sort of tension stability theorem, a stability theorem you want to prove, in principle you know what to do. You have your groups, you can get this building, maybe you can show it's highly connected, and then you run a spectral sequence. And maybe the spectral sequence really is to give a slope 2 stability. So let me try to give you a sketch of why this happens. So what is a spectral sequence? So there are two versions. One, you have your action on your simplicial object. You can make a double complex by taking a free resolution of your group. Instead of a G, the augmented cellular shapes. Okay. So it's a double complex. It gives us two spectral sequences. If I first take the homology in this direction, because we assume that this was highly connected, this is 0 in the range, therefore it's going to converges to 0 in the range, depending on the connectivity of X. And on the other hand, if we take the other spectral sequence, the other spectral sequence has E1 Q, we're going to take the homology in this direction, construction, we keep this one fixed. And now we just saw what is, this is our, just put it up here, I don't know if you can still read it, CP. This is CP of x, or Gn. And the P simplices was Gn mod Gn minus P minus 1. So this is the homology HQ of G with coefficients in CP G, which is G modulo the stabilizer of a P simplex, and by Shapiro's lemma, this is the homology of the stabilizer of a P simplex. Okay, and what does this look like? 0, you have minus 1. At minus 1, this is a trivial coefficient. You have the homology of your group. You have HQ of P. Here you're going to have HQ of the stabilizer of a 0 simplex. And this will be your stabilization. Construction. You know your spectral sequence converges to 0, and you want to argue that this is an isomorphism. You're going to argue surjectivity by saying nothing else can kill it, can kill this term, and you'll argue injectivity by saying nothing else can kill this term. So you have to look at what could map to this. And if you start looking what is here I have HQ minus 1 of stabilizer over 1 simplex. Here I have HQ minus 1 of stabilizer of 2 simplex, etc. And the slope 2 is really showing up because you want to show injectivity, you're going to have to argue that this one is 0. You'll have to argue that nothing else can hit this one. So what could potentially hit it is this thing. And what you see is Q has gone down by 1 and the P has gone up by 2. So the inductive step, you need a slope 2. A slope 2 inductive step. That's a sort of whatever the connectivity of this X influence, sort of when you know the vanishing happened, but even if that's very high, you'll be stuck with your slope 2 in this situation. I'll give you a version 2 because it's sort of, there's a trick which is good to know, and because it's closer to what we do for the improved range. The version 2 is you use, as a double complex, you use the cone of the map you are interested in, but tensored with these chain complexes. So, e.g. tensor over G, tensor G, mapping to G, we can call it suspension G, tensor over suspension G, CP X suspension G, where G is the orthomorphism group of some guy, E, let's call it, and then suspension G is the orthomorphism. In our situation, we use this. We do whatever plus your stability, whatever you are interested in doing. so this will have homology relative groups instead of these groups. And so there's a trick which is so we get a similar looking spectral sequence with relative groups, relative homology instead of what we had before. And here there's a trick, which is I think comes to this island from Wire's paper, which is that if you, and I'm going to write something which is a little bit wrong, but I mean, where you have to be very careful what you actually mean. But if you look at the homology HQ, so in the spectral sequence you will have something that looks like this, a relative homology. In this place, instead of the homology of G, you'll have the homology of some relative homology. And so here I have to be careful what this map is. But suppose I define this right, then maybe I have a map to this relative homology where I have to suspend it once more, and maybe I could do this once more. And so this is be careful about the map. But in the sort of situation we will be in, this composition will be 0. And so if I play the exact same argument where I try to argue that this map is maybe surjective, maybe isomorphism, so in particular, if both maps are surjective, then this guy is 0, HQ sigma 3G, sigma 2G is 0, and if both maps are isomorphic injectives, HQ of the first one, sigma GG is 0. And so this is again now a D1 differential at the very same place. And if you look at, we'll have again some sort of induction argument. If you look at what this requires, this will give you, inductively give you a slope 3. This was the wrong one to do, but this one gives you a slope 2. So this is just as good as this. So that's what it is. So then you have to give up on that. Well, no, you don't give up, right? So there are two possibilities here, right? So either you say, okay, I don't get more for free, but maybe I can get more by working, right? So I could try to study the differentials or something, I don't know. Yeah, or maybe I have to do something slightly different. But so okay, we don't give up. Okay, but we start thinking about what should we do? How could we have a slope one? So there's a first problem. Problem number 1. Well, I sort of pushed away a little bit. I didn't talk much about this connectivity of this building, but of course my whole argument to begin with, I had this vanishing in a range. The range has to be big enough that it's relevant to the stability I'm talking about, right? So problem number 1, we need a, so we want slope. Right. We need a slope 1 connected building. Otherwise, this is totally useless. Okay, and we only know slope 2 connectivity for these canonical buildings. In the case of vector spaces and vector spaces. Okay, so that's a bad start. Actually, the building, I said, was there, happily given to us. We actually can't use it. I don't think I know that it is not interconnected. But anyway, but you know, well, I've been using the word building on I did it on purpose. I mean, we all know the classical building. The classical building is the classical building. It's a poset P of E is the poset of non-trivial subspaces of a vector space. This is dimension of E minus 2 connected. This goes back to 6. So this is slope 1. This is our genus, so this is slope 1 in the genus. Okay, so this one is pretty good. In fact, it is co-macaulay of dimension V minus 1, of dimension V minus 1, which means that i.e. also all intervals in the posets are spherical. So the dimension of this thing is dimension V minus 1. It's connected all the way up to its dimension. So it has only non-trivial homology top and bottom, that is what we call spherical. But also if you take any subinterval, that also has this property. They also do this. Okay, so that's a good one. And for position, so we prove if you take P, if now P iso of E, so now we have our form space, you can take the posets of subspaces W in E such that W is isotropic. Then this is also co-macaulay of dimension genus of E minus 1. Okay, so that's our slope on buildings. Good. So we again have buildings, and then we have to worry about, we have connectivity, we have to worry about stabilizers. We sort of know the stabilizer will be wrong because we have the wrong building. But we have to look at how bad they are. Okay, so this is problem number 2. stabilizer, the W in DV, so let's do the vector space case first. We look at the stabilizer of a W, we have an action, so the action here, V, acts here happily on the subspaces. What stabilizes a subspace? Well, if I stabilize a subspace, I definitely have a map to GL of the subspace. I can restrict to that subspace. And well, this has a kernel which is some affine group, which is the linear maps that restrict to the identity on W. Okay, so this is a new group. So this is bad for our induction, because our induction we just wanted to apply to our previous group, but now we have changed groups. Okay, and if you look at W in E iso E, our automorphism group of E, and acts on this, where we look, what's the stabilizer of W? Well, W is still a subspace, and its lemma tells you that actually, if there's no radical, this is why I'm using it's non-degenerate, you'll actually have a surjective map onto GL of W, and the kernel will be some relative group. So it's A iso C W, some new group. Okay? We're not done with our problems. So this is problem number 2. So problem number 1 wasn't really a problem. 2 is a bit annoying. Problem number 3, E, PV, and E iso E are posets. Okay, so if you remember, we had simplicial sets or simplicial complexes and these sorts of things. And now I have posets. Well, it's a big deal. I take the realization I have a happy simplicial set. Yeah, but I don't want to do this, right? Because my P simplices are now sequences of stuff. And I don't, I want to talk about elements in the posets. I don't want to start talking about the simplices in the realization. Okay. So my cellular chain complex from before, I'm going to have to replace it by something a little bit more fancy. But they are, luckily they are Cohen-Macaulay posets, which is necessarily here. And so from these you can create, so you can create an acyclic chain complex, not acyclic, no homological one. A chain complex. You can compute. You have a chain complex computing the homology of these things, which is C R and the R. It's going to have. So this. So the sum over W in ER, a rank R. So these are not just Cohen-Macaulay posets; they are ranked. What is called ranked Cohen-Macaulay posets. So rank means that every chain has every maximum chain has the same legs. So I can talk about the rank of an element. It makes sense. So you can look at all the elements of rank R, and then we prepare the reduced homology R minus 1 of the lower interval of W. Okay, and this so computing the reduced homology of P. Okay, so this will replace our cellular chain complex. But this is a slightly more complicated object. Note P. So if I PV, so I'm in the poset of subspaces of V, lower interval of W, well, that's not so difficult. It's subspaces of V that are also subspaces of W. This is the W. Okay, so it's again one of these things. And what is this? This is the top homology of this guy. This is also what is known as the, this is J of W, this is what is known as the Steinberg module. So this inherits an action. It's a module over J W. Okay, but the other node, which is a happy node, also E smaller W, is actually the same guy. P W is a general linear building. Why? Because this was the process of isotropic subspaces of E, and if W is already an isotropic subspace, and I'm looking at guys that are subspaces of it, then they're also isotropic. So this is again a general linear building. So I'm going to have a more complicated chain complex, but in both cases, what will show up is Steinberg modules. The same Steinberg modules. Okay, so this one was not a problem, so I'm going to take it away. Okay, so we have these two issues that well, the stabilizers are complicated, and the chain complex we're going to use to do this when we write our double complex is also more complicated. It has these non-trivial modules showing up. And so, the fact is that problems 2 plus 3 has a which okay. So they cancel each other. Why do they do that? To help. How? Okay. So what will happen? So remember. So what's the idea? Remember, we have this. We control. We do the spectral sequence for the cone. So we do this relative spectral sequence, relative version of the spectral sequence for the cone, and we do the same thing, right? So G, and say over G, and then this chain complex there now, mapping to the next one, and we need vanishing of things like AH, maybe then the first one will be something like this, right? HQ minus 1, I'm looking at the row below, I need something from the row below to be 0, and then this will have stabilizer, let me just say I, HI, stabilizer of some WP, some rank P element, stabilize in suspension G, stabilizer for G of, well, really the same WP, like the map from one complex to the next. This is the building for one vector space, this is the building for a bigger one. It is the same subspaces we will be looking at. We will just be adding some stuff. And then there will be G, J of, there will be a non-trivial coefficients. Maybe I will do that. What to do? Okay, I did that a little too quickly. No, that was what I wanted to write. Okay. So one group, the big group, WP, the smaller group WP, and then this J WP coming from the chain complex. So this is the same, so we're using Shapiro's lemma as before. The only thing is we have a non-trivial module here. Wasn't there. Okay, and then what do we know about these stabilizers? Well, they fit into short exact sequences like this. Okay, so the only thing we can do is to say, well, we use the Cauchy-Serre spectral sequence for the short exact sequences. Okay, Cauchy-Serre spectral sequence for the short exact sequences. S is above, that are still over there, and that will have E2 PQ is the homology phi of, well, what's at the bottom there, G and W. This is my WP, right? This is the thing I'm stabilizing is the same on both sides, note, with coefficients in HQ of A. So let's do maybe this one, A, V, W. Yeah, this is the suspension V, right? This is the big V relative to A, the smaller V, W, with coefficient in J, W, P, everywhere. Ah, but P is a different P. Okay, and now we notice that these groups in both situations, they are things that are the identity on WP. They don't act. Okay? Trivial action. Trivial. Aha. So let's go. H, S, E, M, WP with coefficients in H, T, A, suspension, V, W, A, W, answer. Okay, and this will happen in both situations. And now here's where we win one. Okay, two cases, case one. S is non-zero, then T, if this was our HQ, now I can call it Q, then T is strictly smaller than the degree we are interested in, because the sum of these two is Q, okay? And so, and you know, we get a vanishing of this guy by induction. So it requires less than it did before, right? And on the other hand, if S is 0, then what we get is HS GL WP with coefficients in this Steinberg model, and this is known to be 0. Is the Steinberg convergence. We were really lucky. So the lucky thing is, well, you can already see, you know, if I do this for these other groups, I have the same situation. It's the same Steinberg invariance showing up. Okay. The only issue that I have not mentioned, which is really the hard work, is actually we need everything to work also for these new groups that show up, all these relative groups showing up. So we need the buildings for the relative groups, we need the Steinberg vanishing for the relative groups, we need everything, those also these bloody sequences for the relative groups. All of this is very painful, but everything works. And so it does fit together, and that's it.
Questions?
So Suslin also proves.
Oh, I forgot, yeah.
Well, what did he do? Did he do the same thing?
Suslin, I don't know. Actually, this is where the assumption is used. Yeah. Suslin.
So Suslin also proved the stability range for GLN at least. Is that the same method?
No. That's only for infinite fields.
And that's infinite fields. Yeah, so they exist. Yeah, yeah, infinite fields, also for the other groups, infinite fields, there are other proofs. I mean, you don't, the thing is, infinite fields, these relative groups become easier to study, so you don't have to go through. Yeah, so there are, I mean, yeah, you're right, so Sprehn, but there are also for the symplectic unitary, these are known by other means.
For rings with many units.
Yes, exactly, yeah.
Any more questions?
Is there another class of rings who knows that the slope is neither 1 or 2 or somewhere in between?
Yeah, I don't know. I mean, you know, originally we were trying to generalize Jalen to rings of some class, and at some point we gave up because I don't know, we couldn't get anywhere. I think one probably expects that one should be able to do better than slope 2 in some cases, but
I think you already answered this question at the end, but could you say anything about F2 more than anything better than the original estimates?
no,
In other
yeah.
words,
I mean, it really
end
breaks
up at
down,
the
you
end,
know, like right
makes
here,
everything break down.
because this vanishing is like, you know, it's an, yeah, yeah, I don't know if maybe one knows ways.
So, for example, if you allow yourself to change coefficients with F2 coefficients, the standard module is projective and irreducible, so that goes to good. So for coefficients in F2, it's sort of inevitable. We go around a little bit. Either at 2 or away from 2, something is still true. Think for a minute about which one it is. Yes. Yeah. In one case, you can still do something.
So Oscar is thinking